Hello everyone. In the lecture today, we will continue the introduction about the rest contents of the acetal method applied for the flexible pavement design. Here are the design factors we have to consider for the acetal method. In the previous lecture, we introduced the design life, traffic loading, and reliability. In this lecture, we will focus on the introduction about the serviceability, environmental effects, material property, and drainage system. The design serviceability loss is one of the most important factors we have to consider for the acetal method. The equation here shows the estimation of the serviceability loss, which is the difference between the initial serviceability index P0 and terminal serviceability PT. Usually, for the serviceability, the value varies from 1 to 5, and the initial serviceability for the rigid pavement is usually set as 4.5. For the flexible pavement is set as 4.2. The terminal serviceability index for the flexible and rigid pavements are the same, but they are different for the road types. For the major roads, the value of PT is set as 2.5. For the other types of road, it's set as 2.0. Usually, the serviceability loss is determined by the traffic loading and the climate information, while in the acetal method, we will usually only consider the traffic loading impact. The figure at the bottom of this page shows the changes of PSI over time. Basically, as time passes, the value of PSI will be smaller. Once PSI reaches to the terminal serviceability level, we have to conduct the rehabilitation or reconstruction of the pavement structure. Usually, the terminal serviceability level is determined based on the percentage of people stating unacceptable to the pavement structure. At the PT value of 3.0, there will be approximately 12% of people will not accept the pavement performance. By reducing the terminal serviceability level, the acceptance rate will be increased dramatically. At PT equal to 2, almost 85% of people will not accept the pavement performance. The material properties is another important factor we have to consider for the acetal method. Usually, we will consider the subgrade effective resilient modulus to measure the strength of the subgrade soil. The resilient modulus is measured based on the lab experiment, and it's defined as the ratio of the cyclic stress and the recoverable strain from the test. In addition, in the real-world implementation, we need to consider the seasonal variations of the resilient modulus, which is caused by the changes of the temperature and the moisture contents across the whole year. And we have to adjust the variation for the resilient modulus. The figure here shows the seasonal variation of the resilient modulus over 12 months. Here we can see that during the time of freeze, the resilient modulus will increase a lot, while at the period of the critical thaw, the value of MR will be dropped dramatically. And after that, it will recover back to the normal value during the period of the thaw recovery. This variation should be adjusted for us to find out the adjusted MR values for the design of the flexible pavement. The adjustment of the subgrade resilient modulus can be conducted based on the relative damage, UF. Actually, the value of UF is estimated as the function of the resilient modulus. With this function, we can find out the relative damage at each month of the year. And then we can find out the average relative damage for the whole year. With this average damage level, we can then record the equation here to find out the adjusted resilient modulus. Now let's check one example to see how we can estimate the adjusted resilient modulus. In this example, we are provided with the subgrade resilient modulus of each month in 1 year, which is shown in the second column in this table. And then we can apply the equation UF equal to 1.18 times 10 to the power 8 times MR to the power minus 2.32 to estimate the relative damage. For example, for the January, we have MR equal to 15,900, and we can call the equation to find out UF as 1.18 times 10 to the power of 8 times 15,900 to the power minus 2.32, which will give you the value as 0.02. You can also use the figure on the right to find out the value of UF. With that, you will find the point here, which is for January, and the relative damage is 0.02 as shown in the scale on the right. Similarly, you can find out the relative damage for all the other months, and then we can find out the average relative damage UF bar as 2.11. With this information, you can solve this equation. UF bar equal to 1.18 times 10 to the power 8 times MR bar to the power of minus 2.32 by giving the value of UF bar as 2.11. You can solve the value of MR bar as 2,200 psi. Or you can go to the figure on the right with the value of UF bar as 2.11, which will be some point here, and by checking the value on the left, you can get the adjusted resilient modulus as 2200. So that's the way for us to use the resilient modulus on each month to find out the adjusted resilient modulus for the whole year. Determining the thickness of the pavement layers is the major task of the AASTO method. Actually, in the AASTO method, the pavement thickness is determined based on the structural number. Start from now, we will introduce how to use the structural number to estimate the thickness of each pavement layer. The figure here shows the typical layers applied for the flexible pavement, including the surface course, base course, and the subbase course. The structural number for the whole pavement is set as Sn, and it could be estimated by the equation here, where Sn equal to the summation of Ai times Di times Mi from I equal to 1 to n. In this equation, Ai is the structural coefficient for the ice layer, Di is the thickness, and Mi is the drainage coefficient for the ice layer. Usually for the surface course, say I equal to 1, we have Mi equal to 1. In addition, in this equation, n is the number of the layers. Usually we set n equal to 3. With that, we have Sn equal to A1 times D1 plus A2 times D2 times M2 plus A3 times D3 times M3. And this equation is applied for us to find out the thickness, which is D1, D2, and D3 for the flexible pavement. The figure here is applied for the estimation of the structural coefficient A1 for the surface course. In this figure, the horizontal axis is the elastic modulus of the surface course, and the vertical axis is the value of A1. Basically, with a higher value of the elastic modulus, the structural coefficient A1 would be larger. This figure shows the estimation of the structural coefficient of A2 for the granule base. Basically, in this figure, the axis on the left is the scale for the value of A2, and it could be determined by the value of CBR, R values, the Texas triaxial test result, or the resilience modulus. For example, if you find the CBR value as 35, then the value of A2 will be 0.1. This chart is applied for the estimation of A3 with respect to the granule subbase layer. The chart here is very similar to the one applied for the value of A2. Basically, in this chart, the left axis is the scale for A3, and it could be determined based on the value of CBR, R value, Texas triaxial test results, and the resilience modulus. For example, if CBR equal to 23, then we can find the value of A3 as 0.1. You can also find out the value of R or the resilience modulus and use them to determine the value of the structural coefficient A3 for the granule subbase. The table here shows some typical values about the structural coefficients for the surface course A1, base course A2, and subbase course A3. Usually A1 is larger than A2 and A2 is higher than A3. Also for the base course, if the materials is treated with asphalt, then the value of A2 would be very high, and the coefficient can drop to a very small value if the portion of the sand clay is very high. Moreover, for this table, you have to use the imperial units instead of international system of units. For example, for the hot mix asphalt layer, 0.44 represent 0.0173 per 1 millimeter. In the AASHTO method, we also need to think about the drainage condition of the pavement structure. As we defined in the previous lectures, the quality of the drainage system can be determined by the time when the water can be removed from the pavement structure. If the water is removed within 2 hours, we say that the quality of the drainage is excellent. If the time is more than 1 month, then we say that it's poor. And for the estimation of the structural number, the drainage coefficient of the pavement structure should be determined by the quality of the drainage system and the percentage of the time that the pavement structure is exposed to the moisture level approaching saturation. Usually with a smaller number of the percentage and the higher quality of the drainage system, the coefficient will be larger. And if the quality of the drainage is low, then the coefficient will be smaller. With this information, we can then summarize the steps for the design of the flexible pavement in the AASHTO method. In the first step, we need to determine the effective resilience modulus of the subgrade. And then we will select the design serviceability loss, which means we want to find out the initial serviceability index and the terminal serviceability index. In the third step, we will estimate the total number of the 18 kilopound equivalent single axial loads (ESAL) for the design period. And then we will select the level of reliability and the overall standard deviation. With that, we want to determine the pavement structural number, Sn. Finally, we will use the relationship between the structure number and the thickness to select the layered material type and determine the layered thickness. Within all the steps in the design of the flexible pavement, the estimation of the structural number is one critical step. Actually, the estimation of SN can be conducted based on the normal graph, which is shown in the figure here. The implementation of the normal graph is quite straightforward. Now let's check one example to see how we can use the normal graph to find out the value of the structural number. Assuming that we are provided with the ESAL of the design period as 5 times 10 to the power of 6, the reliability is set as 95%, and the standard deviation is set as 0.35. The resilient modulus is measured as 5000 psi, and the serviceability loss is set as 1.9. Then we can start from the axis on the left and go to the right to find out the value of the structural number. We know that the reliability R is set as 95%, which is 1 point in this scale. And the standard deviation is set as S equal to 0.35. You can find the point in this axis. And then you connect these 2 points and draw a line to reach an intermediate timeline. That is TL. With that, we find the intercept. That's 0.1. And then we have to check the ESAL. In this example, ESAL is 5 times 10 to the power of 6, which is a point in this scale. And connecting point 1 with the value of ESAL, we can draw another line, and this line will be extended and reach to another turning line. And we get another crossing point 2. Now start from point 2, and we can use the effective resilient modulus, which is MR. The value of MR is 5000. We can get the point here, and then connect 2 to the value of MR and extend the line to the graph. The intersection from the line to the y-axis of this graph would be a 0.3. That's the point we want to find. Then in this graph, we will use the value of serviceability loss, which we say is 1.9 in this example, to find out the line we have to use. The line should be between 1.5 and 2.0. Then start from the 0.3 and find out the horizontal line to the line with delta psi equal to 1.9, and find out the horizontal value. The value at the x-axis would be the structural number. In this case, that is Sn equal to 5.0. So with the information of ESAL, R, SO, MR, and delta psi, we can then find out the value of Sn. With the estimated structural number, we can then estimate the thickness of each pavement layer. We will start from the surface course to the subbase course. First, for the thickness of the surface course D1, it should satisfy the condition here. D1 is larger than Sn1 divided by A1. where SN1 is a structure number estimated based on the base course resilient modulus. And the value SN1 divided by A1 is actually the minimum thickness applied for the surface. With that, we need to select an appropriate value, D1 star, to satisfy this condition. And the product of A1 and D1 star is set as SN1 star, which is the actual of the designed structure number for the surface course. And it should always be higher than SN1 as what we estimated from the monograph. Then in the second step, we will estimate the thickness of the base course D2. From the equation for the structure number in the previous pages, we can find that D2 should be applied to satisfy this equation, where D2 is higher than SN2 minus SN1 star divided by A2 times M2. In this formula, SN2 is a structural number estimated based on the subbase resilient modulus. And then we have to select an appropriate value of D2, which is a D2 star, for the estimation of SN2. And we need to make sure that SN1 plus SN2 is higher than SN2. Finally, we can go to estimate the thickness of the subbase course D3. And D3 should satisfy the condition D3 star higher than SN3 minus SN1 star plus SN2 star divided by A3 times M3. In this formula, SN3 is a structural number estimated based on the subgrade resilient modulus. And here, these three steps will be the way for us to find out the thickness for each pavement layer. In addition, there are some typical minimum thickness applied for the asphalt concrete surface layer and the aggregate base layer. Usually for the traffic less than 50,000, the asphalt concrete layer should be higher than 1 inch, and the aggregate base should be higher than 4 inches. While with the increased traffic, the minimum thickness of the asphalt concrete layer and the aggregate base layer should all be increased. When the value of ESAL is higher than 7 million, the asphalt concrete layer should have the minimum thickness of 4 inches, and the aggregate base layer should be higher than 6 inches. And this minimum condition should be applied with the previous analysis about the thickness based on the structural number. Now let's check one example to see how we can use the Ashton method for the design of the flexible pavement. In this example, we assume that there's a flexible pavement with 3 layers: surface layer, base layer, and subbase layer. The figure on the right shows the resilient modulus, layer coefficients, and the drainage coefficients for the pavement. Also, we are provided with the ESAL as 18.6 times 10 to the power 6. The reliability is set as 95%. Standard deviation is 0.35, and the serviceability loss is set as 2.1. We want to find out the thickness of the 3 layers, D1, D2, and D3. In order to solve this problem, we first need to identify the values of the structural number for all the 3 layers. Let's first see how we can find out the structural number for the first layer, the surface layer. We will use the monograph for the estimation of the structural number. From the problem, we know that the reliability R is 95%, which is 1 point in this scale, and the standard deviation S0 is 0.35, which is the point as we show in this scale. And then we will connect these 2 points and draw a line which will reach to the first turning line and have the point 1. After that, we will try to find out the value of ESAL, which is in the 4th scale. The value is 18.6 million. So we can find the value around a point here. And then we will connect the second point, the point 1, with the ESAL. And reach to the second turning point. With that, we will use the effective resilient modulus based on the elastic modulus of the base layer. So we have MR equal to E2, that is 30,000 psi. In this case, that will be the point here. Then we can try to connect point 2 with the point in the resilient modulus scale. And it will reach to the third point. With that, we can identify the line we need to choose based on the serviceability loss, which is a 2.1, and that's a point, a line below the line of 2. So we can try to find out the point and identify the structure number. In this case, we have structure number SN1 equal to 3.2. So that's the way for us to find out SN1. If we want to find out the other two structure number SN2 and SN3, you need to use a different resilient modulus. The other values are the same. So for SN2, you have to use the resilient modulus equal to the modulus of elasticity at the subbase layer, that is 11,000. So MR equal to 11,000. With that, you can find out the structural number as 4.5. Similarly, for the structural number for the subbase layer SN3, we have to use the value of resilient modulus as the modulus elasticity at the subgrade layer. So we have MR equal to 5,700. By using this value, we can find out the structural number as 5.6. And with this 3 structural number, we can then go to the estimation of the thickness for the 3 layers. For the first layer, which is the surface layer, we can use the formula we defined previously as D1 star should be higher than SN1 divided by A1. We know that A1 is 0.42 and SN1 is 3.2. So we have the minimum value as 3.2 divided by 0.42. which is 7.6 inches. We can choose any value that is higher than 7.6 as the thickness of the surface layer. We'll choose the integer number. So we set a D1 star as 8 inches. With that, we can get the value of SN1 star as A1 times D1 star. Then we can go to estimate the thickness of the second layer, the base layer. Similarly, we will use the formula D2 star. It's higher than SN2 minus SN1 star divided by A2 times M2. In this case, we have SN2 as 4.5 minus SN1 star as 0.42 times 8 divided by A2 is 0.14 times M2 is 1.2, which will give us the result as 6.8 inches. Similarly, we will choose any value that is higher than 6.8. We will choose an integer number D2 star as 7 inches. And we will then use the condition SN1 star plus SN2 star higher than SN2. In this case, we can just choose SN2 star as A2 M2 times D2 star. Then we can go to estimate the thickness of the subbase layer. Well, we will call the condition D3 star higher than SN3 minus SN1 star minus SN2 star divided by A3 M3. That is 5.6 minus 0.42 times 8 minus 0.14 times 1.2 times 7 divided by 0.08 times 1.2. And this will give us the result as 11.1 inches. We can actually choose any value higher than that. So in this case, we can choose the value as 11.5 inches, or you can choose 12 inches. Also, you need to double check this one with the minimum thickness requirement we specified in the previous page. For the surface layer, the thickness is set as 8 inches and the subbase layer is set as 7 inches, which are all higher than the minimum requirement. So we say that the design about the thickness of the 3 layers are appropriate for the flexible pavement based on the predetermined conditions of the traffic and the drainage information. So that's all about the lecture today. Thank you very much for your attention. With that, we finished all the contents in the H2 method. In the next lecture, we will introduce the flexible pavement design in Ontario.